Inductive reasoning. Inductive reasoning means we are looking at a few particular examples of a certain situation and try to guess what's happening only with that information. So it's a matter of guessing of what's happening, which is different from actually a proof. So here's an example. Find a pattern for this sequence of numbers and use that to get the next number in the sequence. If we look at the difference between any two numbers, any two consecutive numbers, seems like 3. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11 likewise. So to get the next number in the sequence, we have to add 3 to 20 and we get 23. Now if you carefully look at this, we only have about 7 entries in this sequence, and we have to guess what the sequence is from those only 7 entries. So we only look at few examples. Therefore this reasoning is inductive. That means we are simply guessing what's going on. Here's another example, a very famous sequence, Fibonacci sequence. If you look at a lot of places like YouTube, you will see documentaries on this sequence. You come across this sequence in nature, a lot of natural places. So it's very interesting, and it has a certain pattern. If you carefully look at this, at first looks like these numbers are random, but you get the next number by adding the two previous numbers. 1 plus 1 is 2. 2 plus 1 is 3, 2 plus 3 is 5 likewise. So to get the next number in the sequence, we need to add the last two numbers in the sequence. 21 plus 34, which gives us 55. An unproven result, a guess we make on a certain situation, we call it a conjecture. This is a keyword you need to remember. You will see it in problems in your quizzes and exams, and also homework. Next type of reasoning we come across in mathematics is actually the more widespread reasoning is deductive reasoning. Deductive means simply proving the result. So if you prove a given result, it's not a conjecture anymore, it's a proven result, and that method of proving we call deductive reasoning. Here's an example which uses both the methods. Let me quickly read the problem. We are supposed to do a bunch of things to any given number. Multiply first by 4, then add 8 to the result. Divided that by 2, subtract 4. We need to do this process to these three numbers, 3, 7 and 10. We'll start with that. So we are starting with 3. Multiply by 4, we get 12. Add 8, we get 20. Divide by 2, we get 10. Subtract 4, we get 6. So starting with 3, we do all these things, we end up with 6. For 7, we do the same things. First we get 28, multiplying by 4. Add 8, 36. Divide by 2, 18. Subtract 4, we get 14. 10, similarly, multiply by 4 gives 40. Add 8, 48, divide by 2, 24, subtract 4, we get 20. So let's look at B. Part B says, obtain a conjecture relating to the initial result, and part C says, whatever we get in part B, prove that result. So let's go to part B. Let's summarize what we got in A. For 3, we got 6. At the end. Starting with 7, we got 14. Starting with 10, we got 20. Carefully think what kind of pattern we get. For example, what if we start with 25, or any other number for that matter? Let's say 25 for example. 25 looks like we are going to end up with 50. Something like 9 looks like we are going to end up with 18. So the pattern is, whatever the number you start with, your result is going to be twice that number. We can write it this way. So the conjecture is going to be selected number multiplied by 2 gives the final result. You can write it in words any way you want, but it has to be clear. You start with a number, you get twice that number in this particular example. So there are things which are not acceptable as conjecture. Now this conjecture exactly tells me what we get, provided you tell me what number we are starting with. 7, it tells me 14. 22, it tells me twice 22, 44. Here's an example of what is not acceptable. Any number given gives an even result. That doesn't work because if I give you a number, you cannot tell me exactly what you get as a result. 15. Getting an even number doesn't mean what that even number is. So that's not acceptable. There are a lot of unacceptable answers, like the result is larger than the starting number. Wouldn't work because there are so many larger numbers. There are so many possibilities. It's not clearly telling me what I'm going to get. Now let's prove this result. Now remember, proving means we have to make sure it works for every number. Generally we only use the natural numbers. So it has to work for every natural number. If you pick one number at a time, nobody ever for the eternity is going to finish it. So that's where the power of actually algebra comes in. Algebra tells us how to do it for all the numbers. So let's try to prove the conjecture. So proof, let's pick n, which represents any number. If you, from here onwards till you finish the proof, you can only use n. You cannot say let n be equal to 10 or 15 or any other number and do it for that particular number. That's not a proof. Again, you're showing only for that number. So n has to be there. You're doing everything in the algorithm to n and compare the final result. Let's try that. You're starting with n. Multiplied by 4, we get 4 times n. Add 8, we get 4 times n plus 8. Divide by 2, we get 2n plus 4. Subtract 4, we get 2n. So we started with n, we got 2n. And that's twice n. This proves our conjecture. As a note, our conjecture is not actually a conjecture anymore because it's a proven result now. It's not guessing.